Hey, I think people are getting a little bit late as the quarter goes on, but we're going to get started here. Welcome back to a Wildfire seminar series. It's been great to have everyone here this quarter. These are recorded, and if you need to see recordings from the past seminars, let me know. Reach out to me. I am pleased to have this week's speaker, who I can introduce because she is both a friend and she meets at the intersection of my two interests, environmental fluid mechanics and wildfires. And it's such a treat to have her back with us. She's on the other side of the bay at Santa Clara University. We have Hayoon Chung in the house today. She holds a PhD from Stanford in civil and environmental engineering, and also a BS from MIT in civil and environmental engineering, which she earned in 2016. Both her postdoctoral and doctoral work was in environmental fluid mechanics on experimental study of turbulent channel flow over various canopy structures. The different systems she replicates in the experimental setting are focused on environmental applications to climate-induced extreme weather conditions or disasters, example, wildfires. She is currently a lecturer in the Civil Environmental Engineering department at Santa Clara University, and I think you'll really enjoy her talk today to see how basic science or fundamental laboratory science can really lend some insights into this really big problem of wildfires. So that being said, I'm gonna hand it over to you, Hayoon. I'll stop sharing my screen and welcome, and we're glad to have you here today.
Hey, thank you. So I do have a cold, so I might be coughing a lot during the talk, so I apologize for that in advance. And I'll go ahead and share my screen. Is everyone able to see this?
That looks great.
Okay, yeah. So today I'll be speaking about part of my work I did during my dissertation at the EFML, and also my postdoctoral work, which I had many other collaborators, including Laura and Erica. I think Erica is here right now, and the PIs on that project was Nick and Jeff. And I do have an introduction that it looks like a lot of the participants here understand fluid mechanics, but hopefully the ones that watch the recording who are not familiar with turbulence and fluid mechanics might get a better sense of why we did the type of applications that we did. So you might be wondering, what is the relevance of fluid mechanics in wildfire? And so on the left here is a picture from the Dozer line, and the Beaver Creek fire on the right are, I think that was during my third year of my PhD. I was doing a bunch of tracer experiments in a flume. So a flume, if you ever go to Y2E2, you could, if you have a friend in the EFML, you can go take a look at it. But it's basically a water version of a wind tunnel. And you have a tank that recirculates water at the velocity you would like to. So this image you see on the right has flow going from left to right at some velocity. And what exactly is fluid mechanics? You can think of it very simply as how fluids that include both air and water, how they move and the physics associated with that. And for the environment, particularly what I'm interested in is how that fluid might move things. And second, how things might move that fluid. And so if you look at this image on the right, there are many things happening. But what I did was I released blue and green dye upstream and looked at how it moved. So that would be the case in which the fluid is moving these tracer dye. And we are looking at how the fluid will move that tracer dye. And second, you'll see that the structure, there's a lot of structures happening by the dye. That would be the case in which the canopy, so if you look at the bottom there, there are some, we'll go over canopies later, but due to the presence of those canopies and how they move the fluid and cause, later we'll go over turbulence, you can see these structures of the fluid. It's not uniform. There's a lot happening there. If I had not inserted that dye, you would have thought that it was a very calm flowing water. So how can we apply that to wildfires? So we converted these questions into wildfires, wondering how there are canopies whether they're forest canopies and other canopies, that will affect the airflow around them. And second, how will the wind that interact with those canopies, how might they move heat, fire, or embers? So those were the questions that initially motivated us in wanting to apply our expertise on the topic of wildfires. So my background and my work, a lot of the work I did was on canopy dynamics. And so you're wondering, what are canopies? They can include not just terrestrial canopies and forests, but also urban canopies, cornfields, coral reefs, seagrass meadows, wind farms, and mangroves. And what do all of these things have in common? They have a very similar type of flow through them. And so what happens is when you have an array of kind of like in a forest, an array of trees or any array of drag-inducing elements, and you have wind or airflow going through it, what you'll find is that there is very high drag through the canopy and the wind will slow down. But above it, the wind will speed up due to a lot of that air being pushed upwards. And you end up having this two types of flow occurring right on top of each other. And this type of flow is what we would identify as if this array is dense enough, then it'll create a flow that we would consider canopy flow. So if we're to look at this with more of a perspective from looking at velocity profiles, if you have a boundary layer coming in into a canopy, then from the leading edge, you'll have a lot of the fluid being pushed upwards, and eventually you will end up having what we call a mixing layer. Simply put, that just means you have very fast fluid on top of very slow fluid. And the reason why we're interested in this is that it gives rise to what we call turbulence in fluid mechanics, and also as demonstrated by this diagram, you start having vortical structures in the fluid that form right at the interface of the canopy. And so for those of you guys who don't really know what turbulence is, a very, very 1 minute overview of what it is when you have very fast flows, what you typically have is that the velocity is not steady over time. So for laminar flow, you would have, if someone, say, for example, for the campfires, when they estimated that there were some wind speeds that went up to 50 miles per hour, it would not have looked like 50 miles per hour constantly over time, like this laminar flow. Most likely it was turbulent, and it was fluctuating a lot about the mean of 50 miles per hour. That means at any moment in time, it can be much greater than 50 or lower than 50. And so what you see here on this figure on the bottom left is that there is a velocity that will fluctuate a lot across a mean. And we try to characterize turbulence by trying to summarize how much it fluctuates. And due to, so the reason why we're interested in that is in the environment, it affects a lot of how objects or mass is transported. It also, in application to wildfires, we were wondering how that might impact how both heat or embers are transported. So you can think of turbulence as very chaotic motions of the fluid. So here's a video of the image that I showed you earlier, and this is for a canopy system. So this is a water flume, and we have water flowing from left to right, and we have an array of wooden elements that are attached to a board to represent that canopy. And by this, we have that two-layer flow of fast flow over low flow, and it gives rise to these vortical structures. And the way that we characterize this is that there is some size associated with those vortices. There is a frequency, and there is also an intensity. So for those of you guys that are interested, if you plot up the power spectral density of a velocity signal that has been taken in the fluid here, then you would find a peak at some frequency, and that frequency will correspond to the Kelvin-Helmholtz instability, which are those vortical structures. So the motivating question we had was wondering how such canopy dynamics might impact wildfires. So I have a very, very overly simplified schematic here with the core physics that we might be interested in. So if you have a forest canopy and you have a crosswind coming in, then at high enough velocity, you will most likely see these Kelvin-Helmholtz rollers form. And that has been researched a lot by meteorologists who took measurements above canopy tops and found that with high winds, there are these Kelvin-Helmholtz rollers that form. But if there is a buoyant plume that arises from a wildfire, how might those two interact? And the reason why we wanted to look into this is a lot of the research that has recently been done on wildfires did not really consider the instability or the Kelvin-Helmholtz vortices that form and how they might impact wildfires. And the reason why we look at buoyant plumes, so buoyant plumes are hot rising columns of air that arise from the wildfires. They have a strong influence over wildfire behavior, and it's a great way of tracking the behavior of the fire. And for us, it helped us create a really nice model problem that we can try to solve without having to set fire to things in lab. So our system is we have a canopy, we have a hot plume. So that has momentum going upwards with that plume. And we also have turbulence that arises from the canopy. And so without the canopy turbulence, typically the plume and the way it interacts with the wind is often in wildfire literature, how people might try to parameterize a wildfire and the way that it spreads. So there is a non-dimensional number called the Bjorn's criterion. There's also, it is a form of inverse Froude number. You can also look up the Clark's convective Froude number, but it's basically just comparing how strong that plume is. So the plume buoyancy is always vertical, going upwards because hotter fluid will want to rise. And the wind strength is in the horizontal direction. So the balance between those two will characterize the wildfire, with one being that if the wind strength is stronger, then you would have a more bent over plume or fire, and that would, people believe that it might lead to faster rates of spread. As opposed to when it's more vertical, then that means it's more plume dominated. But on the other side of that, that doesn't mean that the fire will not spread because usually when that plume is so strong, it's because it is a crown fire, and it is a much stronger fire when it is buoyancy dominated. In that case, you have a more extreme fire behavior that will start controlling its own climate as well. With that level of plume strength, what you'll end up having is, instead of an externally driven wind coming from the weather climates, you start having wind that arises from the suction from that plume pulling air in. So there's a lot of complications associated with this number. And so there is mixed studies showing whether, depending on the number, if we have numbers of NC less than 2, it's wind driven, does it actually lead to higher rates of spread or not? Studies show mixed results. But our perspective is wondering, but that might not be those two parameters might not be the only parts of the whole figure. What if there is, at such high wind speeds, there should be these vertical structures, and how might that impact the whole system? So we did our experiments in the environmental fluid mechanics lab. We did do it in the flume with water. And so what we did was we matched to actual, similar to real wildfire systems, we matched this non-dimensional number, the Bjorn's criterion, in our water flume while varying our turbulence level. So what we did was, so here is our flume with water running from left to right, and we have our model vegetation that takes up a part of the water column. And the water, because this is in a flume, we have a free surface. And within that canopy, we released a source of a buoyant plume, which was just heated water. So we had a constant head tank that released water at a constant flow rate right at the canopy top. And what we did was we actually changed the location in which they were released. And that's, I won't go too much into that, but that's associated with the development length of the canopy turbulence. So from the starting edge of the canopy, the turbulence that results from the canopy starts out small, and then it'll start growing as you go further into the canopy. And at some point, it reaches some equilibrium state where it'll stop growing. So we actually took advantage of that, and we varied the length upstream of the release point such that we could control the level or intensity of canopy turbulence that will interact with the plume. We also changed the buoyancy, which was the how hot that heated water was, and then that will in turn affect the density of the water. So those were two parameters that we varied across a range, so that instead of just does the canopy turbulence affect it or not, we're able to see the range in which and to the what extent that the impacts can be observed. So here are some experimental methods that we used in order to track the plume. And so the objective of this was to try to observe the behavior of the plume and how it's impacted by varying levels of turbulence. So we used a method called shear imaging. So this arises from the fact that when you have density gradients in your fluid, it changes the index of refraction. So this, you have seen this every day in life. So if you go out on a hot day and you look above the surface of a car or near the ground, you'll see a lot of shimmering happen. So what that is when you have mixed density fluid together, then you have a change in the index of refraction, and you'll see distortion, a lensing effect, and therefore a distortion of the image behind that fluid. And so when we release our hot fluid into our background flow, any object behind it will be distorted. So we placed a random dot pattern behind our flume, and once we, and then had it backlit, and with a camera, we recorded the release plume and over a long duration of time, I looked at how it behaved over time. And as you see on this video here, you can clearly see the regions where that plume is, right? Where there isn't, the random dot pattern looks still, and wherever there is a plume, there is pretty strong distortion. So when we try to track it, you can see this video on the left. When we remove the background, that's how we're able to track those distorted dots, and this reflects the outline of the plume. And using some statistics, sorry, this video is not running. Okay, I'll just keep it as an image. We can try to track the center line as well as the upper edge of that plume. And because this is a video, we can record that over time and see over a long average time, what are some behaviors or statistics related to the plume trajectory that we can back out and try to see what that correlation is with the level of canopy turbulence. So here are two examples. So on the left, we have an example of a very weak canopy shear turbulence. On the right, we have an example of a very strong canopy shear turbulence. The two have very similar cross-flow velocity. And what you see is that on the right, you have the plume that's moving quite erratically. So it's oscillating up and down, whereas the plume on the left looks pretty steady. And so this is an impact purely of canopy turbulence, because the cross-flow velocity was the same. So this makes us wonder, a lot of the models that try to model wildfires will have a plume in their model, but it's just a plume under cross-flow that will be pretty steady. But if we have these canopy structures that come in, what we see is that the plume actually becomes not very steady and it moves up and down a lot. And how might that impact wildfire spread? And so from that study, the main takeaway that we found was that the plume oscillations will occur when you have canopy structures. And although I didn't show you any of the data related to this, we also found that the frequency, so the frequency at which the oscillations occur, agree with the frequency of the Kelvin-Helmholtz rollers. So that the plume will move up and down at the frequency of those canopy vortical structures. It also increased the extent to which it oscillated, also increased with the intensity of that canopy turbulence. Some other results we found was that if there was some rate at which those perturbations moved across, and we found that the speed of the background flow had a pretty big role in controlling the rate at which perturbations or structures within the flow move downstream. I'll skip some of these other key takeaway points because I didn't include them in this study. And I will move on to the next study. So this is from my postdoc work with Erica is here, and Laura, Jeff, and Nick. And after I did the study on the plume, it was not quite as applied, because the most that I can say is that, oh, if this were a real wildfire system and the plume behaved erratically in that way, it would make it very harder to predict wildfire spread, simply because it adds another dimension to the problem. But what we were thinking is that if the plume was oscillating up and down like that, how would that impact how embers are transported in the system? So spot fires is a route of wildfire spread in which it isn't a fire spreading from field to field. It is when a wildfire will release a lot of burning embers and firebrand. And due to both wind and the plume conditions, that firebrand particle is able to be transported upwards and much further downwind, and start a new fire where that is much further from the current fire. And so this is a result of both the background wind and the plume. And the plume helps create buoyancy that allows these particles to be able to get some vertical extent, and then the wind helps it be transported further downstream. And while in the past, a lot of the wildfire management was focused on field-to-field spread, if you imagine fire just moving down a forest canopy, recently, a lot of attention has been more on spot fires. Part of that is because they are very hard to manage, very hard to predict, and they impact the wildfire spread at different levels. And they also have high risk to wildland urban interfaces and structures. And so if you look at the news, recent news about wildfires, you will most likely see a sentence about how far the spotting distance is. So these spotting distances can be up to over a mile. So you can have a fire start a mile downstream or downwind of the current fire. And you can imagine how hard that is as a wildfire manager when you can't really predict where these new fires will start. So I alluded to the wildland urban interface. So this is another motivation behind trying to better understand spot fire spread. Is it's not just wildland that is at risk. It is also residential areas and vulnerable communities that are at risk, because with spotting, even if you think you're far away enough from the forest, you might not actually be when you have these embers that are transported much further than expected, and it can easily start a fire in a residential neighborhood. So our motivating questions are, because we have a background in fluid mechanics, what might the mechanisms be that impact the transport of these firebrands? And of course, in the type of flow environments that we are interested in, And here I have a diagram of the type or the 4 parts of spot fire spread. So the first stage is the generation. So that's how it's generated depending on the type of fuel you have and depending on the type of fire you have. You'll have different types of embers and they'll be lofted to different heights and they'll have different starting conditions. Thereafter, they'll be transported downstream or downwind until it eventually ends up depositing. And wherever it deposits, there will be a chance that it might start a fire or not. And that's what we call secondary ignition. So a lot of research that we don't do, that others do, will be more focused on modeling this burning ember and how it cools and what conditions cause that fire ember to stay burning until the end, and what conditions make it more likely for that to set fire to a new region. And as for after it deposits, there is generally 3 types of spotting: short range, medium range, and long range spotting. And so long range spotting are the ones that I was alluding to earlier, where they're going miles downwind, and it's very hard to predict, and it might start a new fire downstream. But that, while that one is very concerning, and it's usually the more dramatic cases that people are focused on, in addition to that, what a lot of wildfire managers are quite concerned about are the short range spotting cases. And that is closer to the source of the fire. And at that point, it's more like a rain of embers that fall. And as a result of just a shorter distance, so it's more likely to cause secondary ignition. It's closer, so there's a lot more of those embers. And so it's more likely that you'll have a fire. And because it's close to the initial fire, shortly after it starts a new fire, it'll combine with the original fire, creating a bigger fire, and overall lead to much higher rates of spread. So rate of spread for wildfires is the rate at which a fire progresses through whichever direction it's spreading. And so, but for us, what we're interested in is actually the transport. So, and in addition to transport, we're focusing on the turbulence within the flow. So a lot of these models, because it's so multi-physical, you can't model everything. You need to, a lot of people try to choose the piece that they want to work on, depending on what their background is. Ours just happens to be environmental turbulence, and mine happens to be canopy turbulence, which is why I wanted to apply it to this problem. But because we can't model everything, for ours, we will want to focus on turbulence, especially because it's been ignored in a lot of previous literature. People say it's important, but not a lot of people will have been able to do research on it, mostly because it's very computationally expensive to try to simulate. So we have 2 sources of turbulence. The plume is turbulent and the crosswind interacting with the canopies. So those canopy structures I talked about earlier are both sources of turbulence that might impact this transport. And in particular, we are continuing off of my work from before. How might the buoyant plumes interact with the canopy flow and therefore impact how these particles are transported? And what physical characteristics might impact this firebrand transport and how? And how might this change near fuel breaks or wildland-urban interfaces? Here is our experimental setup. So it's very similar to my experiment before. We have a release of a buoyant fluid at the canopy interface. But differently from before is that now we have another release. So we're releasing particles right at the plume exit, such that now we have what we call a particle-laden plume. So this plume and particle system that we will try to understand. And in this case, we didn't use background-oriented clearance system. I can imagine if you have a random dot pattern in the background and you had these particles that you were trying to track, those two don't go very well together. So instead, we dyed the plume this time. And so we tracked the plume with dye, and separately, we tracked the particles using PTV, or particle tracking, I think, velocimetry. And what else was there? So the particles were actually 3D printed spheres. Laura had her background and PhD was in studying microplastics and how they are transported in the ocean. So she was the particle expert on this project. And so we had these particles and we had them all inserted into Tygon tubing that was connected to a syringe pump. And it steadily released the particles one by one over the duration of the experiment at the same time that the plume was being released. And what we controlled was we kept the particles the same across the experiments as these spheres, but we did change the plume momentum and heat. And so we had cases where we didn't have the plume at all and looked at how the particles are transported simply from the impact of the canopy turbulence. We also had a heated plume and a cold plume because we also wanted to look at just momentum alone, as well as momentum and a source of buoyancy. And the third one we controlled was the particle release height. So we had cases where we released the particles right at the plume entrance. So that's the case in which the way that the particle is launched upwards is due to that plume. The plume is pushing it up into the air before it goes downstream. But because we had a lot, because we have a very turbulent system, that source is not a very controlled release. The way that the initial condition that the particles will start with is not steady over time. So we had a second case where we just released the particle higher up above the plume release point, such that all the particles that are released will have the same initial conditions. And then as it moves downstream, then it will start interacting with the plume. And as I have already mentioned, what we were measuring was the plume trajectory and behavior, as I have done in my previous work, as well as the particle trajectory. So the results from the PTV are all position, velocity, and acceleration of the particles, at least until they settle. And so what might that look like? Sorry, that's pretty loud. Sorry if you were wearing headphones. So here, that's what it might look like. This was taken with a video from the side. So this is a case of where we have limited canopy turbulence. So we had a very short canopy and we had blue dye or dyed plume being released. And into that, we are releasing the contraption you see here is a structure to which this tubing is connected. And from that tubing, the tubing is all loaded up with these particles and they're being released one by one into that plume system. I couldn't find the video of the sphere, so these are actually rods. But you can imagine that for the results I'm showing you right now, they should have been spheres. So what does that look like after we process the videos? So what you see on the top is an example of an experiment that we did. And what you see, the contours, the colors that you see are the intensity of the dye. So that lets us know roughly where the plume is and how intense that plume is at those regions. And the particles are moving through, and I actually circled them with these big red circles. And so you can try to see, you can try to see how those particles move in relation to that plume. Laura, Eric, and I, and also our PIs have spent a lot of time just sitting and staring at these videos, trying to understand how the particles are interacting with the turbulent plume. And for this study, this first set of analyses that we did, we were actually interested in the landing distribution. So if these were real embers, and due to these conditions of the background flow and the initial conditions of the particles, how far will they end up from the initial starting point? And so this is trying to go back to the original problem and wondering if you had canopy turbulence, will they impact how particles how far they go, and second, how much they spread. So dispersion would be how widespread the landing distribution is. So here are some results that we had. So for the first set of experiments, I mentioned that we did a more controlled version where we released the particles further upstream so that their initial condition can be same across all the releases of the particles. So we had a strong canopy turbulence and we released the plume, and above that plume, we released the particles. And as the particles settled while moving downstream, it eventually entered the plume and interacted with the plume before settling down to the ground. And so what I have plotted on the right here are landing distributions for the high turbulence case. Whenever I refer to long canopy, that is the case where you'll have these structures and rollers present. And the gray, blue, and red lines correspond to no plume at all, unheated plume, and heated plume. And what we see here is that the presence of the plume will extend as we expected, it will extend the transport of the particles. After we did some analyses of the velocity, we found that this extended transport is due to delayed settling time. So when it enters that plume, the particles will settle slower than if there was no plume, and therefore they are transported further. And second, we also found that the heated plume has an even stronger effect in terms of slowing that particle down. A second result that we found was that the particles settle earlier in the case with strong canopy turbulence. So on the right here, so the solid lines that you see are the same as the first figure, but I've added to that figure the cases of a short canopy. So a case with limited canopy turbulence are in these dashed lines. And what you can see that is that they actually go much further than our turbulence case, which was contrary to what we thought would happen, because we thought those the presence of turbulence in the fluid might keep the particles afloat longer. And so what happened, or what we believe is happening, is that I had some previous work that showed that when you have higher levels of turbulence, the flow reattachment in the wake of the canopy occurs over a shorter distance. So normally, when you have this type of step-like feature in your flow, where you have a flow and then you go down, there is a distance over which the flow will reattach to the new boundary. And what we found was that when there is a lot of turbulence, that will occur over a shorter distance. And so we believe that that was what was happening in our case, where in our more turbulent cases, our particles were landing faster because the reattachment was shorter, meaning that there is a more rapid flux of momentum occurring right at the edge of the canopy, and those particles are brought down together with that flow. And so this was a case in which the particles reflected a lot of what was occurring in the background flow and how it responded to the background flow. But the other case that we tested for was when you have lofting. And this is when I refer to the initial condition of the particles. So in this case, we release the particles right at the plume exit. What that means is that the initial condition of these particles will depend on the condition of that plume at the moment that the particle was released. So you have turbulence from the plume, and in the case with the strong canopy turbulence, you also have the combined effect of the canopy rollers and that plume. And so here I have just for the heated plume case, the landing distribution of the particles downstream of the short canopy, meaning limited canopy turbulence, and the long canopy case. And although there are some other cases where we see very little differences, but in a few cases, we found that there is this difference or some level of extremified distribution. So there are particles that both go further, much further, and also fall out much earlier when you have these strong canopy vortices. And so what is that? What causes this type of more extreme behavior of the landing distribution? So what we went and did was that we took our plume and we have both the, so we track both the particles and the plume. And what we can do is for each particle that is associated with some landing distance, we went back and looked at when that particle was being released, what was the condition of that plume. So if you remember from the previous study, our plume was kind of flapping up and down due to the canopy rollers. So we try to look at the phasing of that movement of when it's moving upwards versus when it's moving downwards. And we try to identify during which phase the particle was being released. And so we sorted the particles that way and looked at the landing distribution again. Now, what you see here on the right are as a histogram of the particles. And the orange, what you see are the sorted particles that were released when the plume was moving downwards. And then the blue bars reflect the particles that were released when that plume was moving upwards. And so what you see is that the particles that were released when that plume was moving upwards tend to be transported further than the ones that were released when that plume was moving downwards. So this helped us kind of understand how those initial conditions matter. So if those particles depend on the initial conditions of the plume for its transport, then those canopy structures will have a pretty strong impact on how they are transported and how they are dispersed. So a quick summary of the results. I have a diagram here on the right. So first, the particle mean transport is dependent on both the plume and canopy reattachment. So that's mean transport. So that's overall how far that particle goes. And the particle dispersion by the canopy turbulence is similar to that of the plume. So although we had expected the dispersion to be higher in the case where the canopy turbulence is higher, simply because the plume itself has such a strong impact on dispersing the particles, mostly by changing or creating such a wide range of distances that the particles can go. The whatever impact that the canopy turbulence had when there is a plume present was drowned out. And third, the inertia of the particles will impact what those particles experience. And so here I have a summary. So if there's no plume at all, then you will see that the particles typically will settle in this first A case where we have that reattachment of the flow, so it'll follow that. But when you have a long canopy and those vortical structures present, they'll have an earlier reattachment. In the case where you have a flow, then you have that upward momentum and buoyancy coming from the plume, so it'll extend the transport and make it go further and delay that settling. But in the case that they are launched by the plume, if it's a steady launching, meaning that there are no canopy vortices, then you'll have the particles be transported by that plume before it settles. But if it's unsteady, then the way that those particles are being launched will fluctuate, and therefore the landing distribution will also become more extreme due to that. So that isn't the end of this work. We are still currently working on that data set. So recently, Erica has published a paper. So if you want to go take a look at that, she took a different perspective looking at our landing distribution and characterizing it from a more data point of view of using K-clustering or K-means to see categorize the particles that would be considered a close settling and a far settling distance, and associating that or analyzing particle velocities to try to understand what might control that. And of course, Laura currently has a paper under review on the impact of the particle shape and how if we had rods and they rotate, how might that impact landing distances and dispersion. And of course, we also have gaps. So these are future work or future analyses that we will work on in the upcoming months. Yeah, so that's it.
Hayoon, thank you so much for your time and thank you for holding your voice up. Hope that this doesn't strain you too much. We have some time for some questions. I have some, which is surprising because I should know this work pretty well, but this is great. Any questions from the audience and comments, maybe even from Erica if I don't want to call her out, but she can comment or question too.
Yeah, if Erica, you want to talk about your work at all.
I will start us off because this is something I actually surprised I haven't thought about before. So I think this whole thing that turbulence sort of changes the dynamic of the casting of the embers is pretty profound. But one thing that comes to mind is the LA fires. And
Mhm.
they found surprisingly that winds, at least anecdotally, the firefighters are used to say 50, 60 mile per hour winds. And for whatever reason, maybe it's the Santa Ana or maybe the fire was so intense, they were seeing 80 to 100 mile per hour winds. So that is something that I don't think you directly talked about. You talked to keeping the crosswind amplitude constant. I'm going to ask you to speculate and not ask you to do any fancy scaling, but if you double the crosswinds, that changes the transport, but that also changes the turbulence. Have you thought about how that might change your results? It seems like those are going to compete against one another, and I'm not sure how they would add up.
I mean, my work, it did do two different flow rates. So I did do it over two. I think it's just I fell in the regime where the results were pretty similar across the two velocities. So it might
Okay.
be different from looking at 50 and 80 miles per hour.
So do you think so? So do you think that then the enhanced wind or enhanced flow is counteracted with the turbulence being enhanced, right? So if you have a large mean flow, presumably you would get more turbulence, right?
Mhm.
But then those are competing against one another. Is that what you think? If you said that you didn't see much of a change?
Uh, no, I don't think they're competing. So I think it's very hard to identify because those aren't the only two parts of a wildfire. So when
Yeah.
it was like when it becomes that intense, I think so a lot of the work I did would be for much smaller fires. So I have a system where I have a point source of fire and I have um, an external forcing. So the wind is external. But a lot of with these wildfires is a lot of that wind is actually created internally by the wildfire itself, and that's not something that I have in my system.
Mhm.
But I think the importance here is that when we are thinking of fires, they do start with the smaller fires um, that are more similar. Smaller fires with very strong wind conditions will
Mhm.
cause a lot of spotting and cause a smaller fire to get really big. But yeah, I think that I don't quite have all the information to answer your question.
Well, no, I think it's a hard question. I didn't expect you. I was just thinking maybe we would do a back envelope scaling, you and me offline about that, because I'm thinking that, change the wind, you change tau, change the turbulence, but then you've got the trends of enhanced turbulence changing, right? The ultimate distribution of the spot fire. Another question I'm not sure you guys have been looking into is, have you translated this back to the real world? I mean, this is the real world, but translated the distances you see these particles going to real embers and thinking about how live the embers might be in terms of how far they might go and whether they would cool off enough and be less prone to starting another fire or not. Have you guys thought about that? Again, trying to cast it
We
back,
have
scale back to the real world?
we have thought about it, but we have avoided it. And that's mostly because that wasn't the intent of our
Hmm.
experiments for it to have direct application. We wanted to more look at these the physical parameters in a situation and see if they have an impact in certain flow regimes. But in terms of because real wildfires, there's not too many measurements that we can try to match. And there's such a wide range that when we did our literature search in the beginning before designing the experiments, it was very hard to identify exactly what we should try to model if we were trying to model exactly what's out there. So we took a approach more of, here are some regimes that we're testing in. And so if people are interested in, then they can go take measurements in real wildfires and try to see if what we observed is something that they might need to be concerned about for their system.
That's great. All right, any other questions before we let Hayoon rest her voice? All right, well, again, thank you for your time, Hayoon. I really appreciate you taking the time. And I think, as I'm biased, but this is fascinating work and really important as we look at not just wildfires, but urban conflagrations as we think about LA, because these
Yeah,
things matter. And I'll just put a plug in to maybe you guys can think about this as another canopy, right? Would be the urban environment itself in the WUI, right?
yeah.
So buildings, homes are another form of canopy. And then so this is relevant not just to forests, but to human infrastructure. So great work. Thank you again for your time. Hope you heal up. Thanks for
Thank you.
everyone's attention. We'll wrap it up next week and talk about Stanford's plans for wildfires because we live in the WUI as well at Stanford. We're concerned about it. So we will have the Stanford team talk a little about what they're doing for a wildfire preparation and risk assessment. Thanks again. See you again next week.